So we have seen that centripetal force is mv omega or m r omega square or mv square over r. Those are three formats of the same equation. Centripetal force is this. Now this is hardly used anywhere. This is mostly used in the chapter of gravitation, not chapter, in the part of gravitation, and you'll see it soon. mv square over r. This one is very commonly used, this equation. So the centripetal force is mv square over r is a very commonly used expression for centripetal force. So what is centripetal force? After you've done circular motion, so you know a uniform circular motion is when something is spinning round and round, and for anything to go round and round in a circular path, you must provide this centripetal force. What for? Yeah.
So it can keep going round and round.
What for? A force is needed.
Centripetal force.
Yeah. Why is that force needed to keep it going round and round? Yes.
So it can accelerate?
So that it can accelerate. Why the acceleration is needed there, even though it's going at a constant speed? Change in direction. So that changing of direction is what requires that force, because a force can cause an acceleration, and acceleration is when something is going to speed up, slow down, change direction, right? So in this case, it's mainly the change of direction that matters, and that is what we call as the centripetal force. Now, when something is going round and round in a circular path, is there only one force acting on it? No. You can have more than one force acting on the same object. I think I gave you the demonstration of me walking straight, right? So when I'm standing like this, how many forces are acting on me? Two forces. You know what they are. The weight acting downward on me, by the earth, and then the ground pushing me up. Now when I walk with a constant velocity, how many forces acting on me? Four forces acting on me. The traction force forward, the drag force is backward, normal force, weight. Those are four forces acting on me. Now if I go at a constant speed and take a turn, during the turn you see how many forces acting? 5 forces. So the 5 forces are actually, the first 4 are the same, and then this additional force, which is frictional force on my feet, pulling my feet towards the center of that circular path. What is applying that force on me? What is applying that force on me? Myself cannot apply a force on me. What is applying a force on me? The ground, the road, the floor is applying that force on me in the form of friction. The force is offered by the floor or the road on me, and that is frictional force. What kind of friction is that? Static or kinetic?
Static.
It is static friction. Why do you say it's static friction and not kinetic? Because you're not slipping. We are still gripped wherever we are, right? Yes, we are changing positions, but even though you're changing positions, you're still gripping at those points. So when a tire is rotating, it is still gripping. The only thing is, it is releasing its previous contact and making new contacts. Is that clear? But that doesn't mean it's slipping. So when a tire slips, that's how it happens. That is slipping action. But that is a gripped rolling action. It's a totally different thing. So rolling of the tires is with the proper grip, so it's a static friction thing. Okay? So how many forces were acting on me when I was taking the turn? 5. And 4 of those forces are already balanced, right? It's only the last one which actually was coming in to help me turn. So therefore, this centripetal force is supposed to be the net force. So the net force acting on an object, net force on an object making a turn is the centripetal force. The net force that's acting on an object is the centripetal force. So centripetal force is not a single force. You get it? Centripetal force is not a single force. Centripetal force could be provided as a result of 10 forces acting on a system. You get it? Now, so what is centripetal force again? It's a force that acts towards the center, making us complete that circular path, right? Now, what is centrifugal force? What's a centrifugal force? Anyone? Just participate, no problem. What's a centrifugal force? Have you heard that term? You've heard the term. Okay, so what is centrifugal force? Yeah.
Force going outside.
Force going outside. What is applying that force on us? When I spin this like that, what is providing the centripetal force? The tension in the string is actually providing the centripetal force for it to go round and round, right? Whether it's horizontal circles or vertical circles. The tension in the string is what provides the required force for it to keep going on. What is centrifugal force here? What is the centrifugal force here? The keys. Pulling on the string? Well, there is no such thing as centrifugal force. There is no such thing as centrifugal force. If you see a term centrifugal force being mentioned somewhere, it is rubbish. There's no force called centrifugal force. Yeah.
And why is it a coined term?
Why is what?
In a coined term that it doesn't exist.
Coined? Say it again, once again.
Coined, as in like existing.
Why is the word existing? Not as a force. You can call it a centrifugal action. A centrifugal action is something that you can say. But not a force. It's not a force. You know, a force is something applied on something. There's no force applied. Then why is it called, why do people call centrifugal stuff? It's because, yes, there is no centrifugal force. It is a lack of centripetal force that makes the object go in a straight line according to Newton's first law. You get it? It is not something that's going outwards. When I spin this key, what is providing the centripetal force? The tension, right? If the tension suddenly is absent, like the string breaks, what will happen to the keys? Flies off? And a tangent, like flies off. So if I'm going to spin it like horizontal circles like this, if the keys are here when it snaps, it will just go straight. Why is it going straight? Because the only force that was making it go change its direction was the centripetal force provided by the tension. And as soon as the tension went, what is happening is it is just going off according to Newton's first law. It has inertia, it keeps going straight and keeping the same state of motion. You get it? So is it going outwards? It's not going outwards at all. It's not going away from the center at all. It's just like flying off tangent. So what is centrifugal effect? Again, I won't use the term force. What is centrifugal effect? It is the tendency of an object to fly off tangents, right? In the absence of centripetal force. That is called centrifugal effect. And you have seen that effect in a car. Yes?
Could you spell centrifugal?
The term centrifugal effect is when the centripetal force.
Can you spell the word?
Oh, centrifugal. This is the same thing. Centripetal, centrifugal. Centrifugal effect is the tendency of an object to fly off tangentially in the absence of centripetal force. So it is a consequence of lack of centripetal force. All right? Now, if I say some examples, and you'll see like how that actually kind of works. Imagine you are, let's say, a passenger in a car. You're sitting on the seat. You're a passenger, okay? The driver is driving and you're just a passenger, and imagine you're sitting straight, and let's say there's no seatbelt, nothing holding you. So you're just sitting on the seat. Now what will happen when the driver starts turning the car like this, okay? So the driver is taking a left turn like this. Now when the driver is taking a left turn, what makes a car make the circular path? Friction. By what on what? By the road on the tires, right? That is making the car go in a circular path. Now what is making, now let's look at you as the object, not the car, but you alone. You are sitting on the seat. Your bottom of the body is in contact with the seat and there's friction there, right? So what is making your seat go in a circular path? What is making your bottom part of the body go in a circular path? The grip on the seat. Is that clear? Because you are gripping nicely on the seat, and you have those bucket seats as well, right? It's not a wooden plank. It's like good fabric. So you are sitting on a seat which is a lot of friction there. A seat is supposed to have friction. So because you're sitting on the seat, as soon as the car goes, the seat goes, and so your bottom also goes along with it. So what is taking your bottom part in a circular path is a centripetal force provided by the friction between the seat and your bottom, right? What about the top part of the body? Top part of the body is not being pulled. Your top part of the body, by inertia, it wants to keep going straight. Right? The top part of the body wants to keep going straight. The bottom part of the body is being pulled and provided the centripetal force to be with the car. But the top part of the body is totally free. And so the top part of the body wants to go straight. Now, so look at that. The car is turning and you want to go straight. So it looks like as if you are moving away from the seat. It looks like that. It looks like you're being thrown out of the car. Why? Because you're trying to go straight and the car is making a turn. You understand that? So because of the lack of centripetal force on the top part of the body, your body wants to go in a straight line. And so there's a tendency that you are getting pulled away. The top part of the body kind of leans this way, right? And that leaning effect is called centrifugal effect. How do you stop that leaning? So when you know that he's going to take a turn, what do? You grab something, right? You grab the neighboring seat. So when you grab something, you are perfectly going fine. Your body's not tilting anymore. Why? What is providing the centripetal force for the top part of the body to keep going now? The tension in your arm, that's it. So you're creating that extra force from the top. So the tension in your arm is what's making it go. Now, if he's going to make a very quick turn, then the tension in the arm, you're not able to grip it properly, so you'll still fall off because your hand is not able to take it. You understand what I'm saying? So what is centrifugal effect? It's a term that is used to say that when centripetal force is missing, the object tends to keep going in a straight line according to Newton's first law, and that tendency to go in a straight line when one of them is going sideways is like something forcing you out. That's it. So there is no force acting on the keys, pulling it out. There's no force. There's nothing pulling the keys out. What is happening is, if the centripetal force is missing, the key kind of flies off tangent, and that is why you think it is actually flying outwards. You think it is moving outwards. Like, for example, if there's some dirt sitting on your bicycle tires, and if you're driving the bicycle, what will happen is the dirt, which is stuck on your bicycle wheel, is supposed to go with the wheel, right? Because it's stuck there. So what is providing the centripetal force for this dirt to go round and round in circles is the adhesion force. Correct? The adhesion force between this and this, like how well it is stuck. Now, when the wheel starts spinning faster and faster, what happens? You're demanding too much of adhesion force, but there is a limit for the adhesion force. Once you cross those limits, what will happen to this thing? Will it like fly off like this? The wheel is spinning like that. So will it fly off outwards? No. What's happening is, if the wheel is spinning like that, if it is at this point that it comes off, then it flies off tangent. And think of this, it's flying off tangent. Look, this is the center, and that is the position. So it's supposed to keep the same distance throughout, but look at the distance. It's increasing. Since the distance is increasing, it looks like as if it's actually thrown outwards. It looks like that. Can you see that? This is a distance that it's supposed to maintain all the time. But now what's happening is the distance is increasing. So it looks like it is being thrown out of the circular path. Make sense? All right. So what is centrifugal effect? It is the outward tendency. What is a centrifuge? Yeah, I think you know what it is. So normally used in a chemistry lab, you have test tubes. If you have a solution prepared and it looks like homogeneous initially, but then you can actually pull the precipitate out, the heavy particles down. All you do is put it into the centrifuge and spin it. So when it spins, this test tube actually is going to spin like that in circular path. When the test tube spins, this is the bottom of the test tube. When the test tube spins in a circular path like that, the heavier particles, they need more centripetal force, right? To be kept in the same path. And because it's a fluid, it's free to move to the outside because of the centrifugal action. Do you get it again? Lack of centripetal force. The centripetal force is missing on those particles, and so the heavier particles will prefer to go to the outside because they're trying to fly away. They're not flying away, but they're trying to maintain their inertia, the tendency to keep going straight. And so they go and settle at the bottom of the test tube. So after spinning it for quite some time, you take it out, you can see a clear precipitate, which is basically the heavier particles, and then a clear solution on the top. You know what I'm talking about? Have you seen a centrifuge? Good. So how those things work is purely on this concept of centripetal force. Now, let's look at some of the examples. So I'll throw some questions and let's see how it works. Now, let's say I have a swing. You know what a swing is? That is a swing. Let's say someone is sitting here and swinging 60 kilograms altogether. The swing is 60 kilograms and sitting there. How many forces are acting on it?
If it's still, there's two.
It's still, yes. There are two forces, which is
Gravity or weight.
the weight of how much is the weight? You can calculate it as you go. Yeah. 60 times 9.81, which is
588.
588 newtons, which is basically the weight. What other forces acting on the swing? The tension. Yeah, it depends on what you're looking at. If you're looking at a person, then it is a normal reaction. If you're looking at the swing itself, the rope, then the tension. The tension is upward and the weight is downward. What do you know about them?
Equal.
They are equal. So you can see that this is just one string and this is one system and the two forces acting on it. Now, if this swing is given a pull, if it's released from here and it is swinging like this now. So now we are going to consider a swinging swing. So it is swinging. Now it is swinging. Let's say it is swinging at a speed of, at this point it's moving at 2 meters per second. At the bottom of the swing, it's moving at 2 meters per second. Draw a good enough diagram, big enough diagram. So if I draw it to this size, that means you also proportionally go with that size. If I'm drawing something only this size, then you don't have to make it too big. That's what. Alright. So there's a 2 meter speed. So the swing is moving, and at the bottom of the swing it is 2 meters per second. How many forces acting on it at that point? Like as it's swinging by, how many forces acting on it?
4.
On this. Ignore air resistance. Ignore air resistance. For the time being, just forget about air resistance. We'll bring it when it is required. Yeah, ignore air resistance. What? How many forces are acting on the swing as it is moving at 2 meters per second at the lowest point?
I'd say 3.
How many? 2. Weight and tension. Anything else?
Centripetal force.
Is it going in a circular path?
Yeah.
So how many forces are acting on?
3. 5.
No, I'm just like waiting. I'm counting the seconds. How many forces are acting on it?
3.
2.
2. Yep, I did.
The same 2 forces acting on it. Centripetal force is not a new force. What is that? It's a net force. That's why I wrote it down here. The net force. You can have thousands of forces acting on an object, but the net force is what we need for something to go in a circular path. Do you get it? So in this case, there are only 2 forces acting. And what do you know about tension here? Is it 588?
Yeah.
If it is 588, what's the net force?
0.
And net force is 0 and it's still making a turn possible? If something is going in a circular path, the net force is not 0. The net force is the centripetal force. Do you get it? So right now you know that this is moving in a circular arc, and I can give you the height of this is say 5 meters. The height of the swing, the total length of the rope is 5 meters. So it is moving in a circular path of what radius? 5 meter radius. I know it's not moving a complete circle, but is this path here a circular structure? Yeah, so therefore at this point it is moving in a circular path, which means there must be a net force. Which way should that net force be? Towards where's the center of the turn?
Side of the top.
Right here. So if the net force of these two is towards this point, what do you know about tension and this weight?
Tension's greater.
Tension is greater. Because it is moving in a circular path, tension is greater than weight. And so what's the net force? Net force is tension minus weight. That's the net force. Tension minus weight. This minus this. You know how you've done the Newton's law problems? The net force produces an acceleration. So you'll take the bigger minus the smaller equal to ma. That's exactly what you're doing. You know that tension is bigger. This minus this is equal to ma, right? So what's the net force supposed to be equal to? The centripetal force. So equate it to mv squared over r. Just equate it to mv squared over r, because you know that is the expression for centripetal force. Now can you find the tension then? Go ahead. Tension minus 588 is equal to 60 times what speed you're going? 2 square over 5. Tell me what is tension.
$636.
636. Everyone is okay with that?
Yes.
So the tension when the swing was at rest was only 588. But on the go, the tension is 636 newtons. It's higher. Why is the tension higher? Because the net force is supposed to be this way, so this has to be higher than this. Question? Yeah.
So when it's at the bottom, there's 2 forces acting on it.
Only 2 forces.
So why isn't there a centripetal force?
That is the centripetal force.
Is that just the tension?
That's why I said centripetal force is not a new force.
Okay.
What is centripetal force? What is centripetal force? It is a net force. It is not a new force. Take care. Good. Centripetal force is not a new force that has to come into existence. It is a resultant of whatever forces are existing already. You get it? It can come in different forms. You can have the involvement of a new force altogether. Yeah, that's possible. But whatever is coming in, the net force is what matters if you want to use this. This is the net force. This is not a new force. This is a net force. All right, now let's look at this one here. At the end of the swing, let's look at this. See, that's why I asked you for a bigger diagram. Now, at this point, see, at the point it's turning around like that. At this point. At the point it's turning around here. Let's find out. How many forces are acting here? How many forces are acting on this? At the end of the swing? Two?
Two, because, yeah, two.
Which ones?
Tension.
The weight is downward. And? Tension. Which way? Now what do you know about tension and weight? It just stopped. No speed. It just stopped. At the end, see, at the end of the path, I'm asking you what is the tension? Is it going to be 588? Is the tension going to be 588 and because this is 588?
Yes. Yes. Net force. No.
Now remember, they're acting at an angle. If they're acting at an angle, things are totally different. Here you could, when this was at rest, you can clearly say our tension must be equal to 588. When something is acting at an angle, how can you say this is same as this? Kind of balance.
Is it mg sine?
Which one? That one?
Or no, sorry, cosine. Yeah.
Where is theta?
Cosine.
That is our angle theta. Is right. If that is our angle theta, look at what I'm doing here. Isn't this angle theta? Now we need to resolve, because there are forces coming at an angle. You cannot just do anything with this unless you resolve and look up for it. So this is one of our axes, and this is the other axis. What is the component of mg in this direction? What's the component of mg in this direction? It is the cosine component because it's adjacent component. So this is mg cosine theta. And what is the component of this same mg in this direction? What is the component of this mg in this direction? Mg sine theta. Now you can just ignore this mg completely because we already split it, right? Because you already split it, you can just ignore the presence of this mg because already we got the two components. Right, so we have tension pulling it this way, mg cosine theta pulling it this way, and mg sine theta pulling it this way. What do you know about this swing? Or what do you know about this person? Is he moving that way or that way at this point? Neither. And is he moving at all? No. So there is no centripetal force requirement towards the center. So what do you know about tension and mg cosine theta? Same. So tension is equal to mg cosine theta. Only at that point. If tension and mg cosine theta are equal to each other, what is the net force? What's the net force? No, I'm saying the whole thing. Mg sine theta is the net force. That is why the thing is not going to stick there, it is going to come back. So what is bringing this swing back again into motion is this component of mg, which is mg sine theta. Make sense? The topic is simple. Not too much work in it, but conceptually you must be very clear. That's why I'm kind of slow with this. So these two are canceling each other out. And you remember, problems can be varied. Now this is just a swing. You can have different problems in different forms coming in, but just concept is this. The main concept is this. Don't get out from this concept. Net force, centripetal force. In this case, it's kind of equilibrium sort of thing. So these are both balanced, but this is not balanced. And that's why it is coming down this way. It is in equilibrium in this direction, but not in this direction. So what's the net force acting on the object at the end of the swing? It is mg sine theta. So if I give you angle theta is 60 degrees, can you figure things out now? Can you tell me how much is tension? If I tell you the angle is theta, 60 degrees, so it will be 588 cosine 60, which is 294 degrees. So that means the tension on the rope is not much. When it was sitting idle in the middle, the tension was 588. When it was moving, it was 636. But when it comes to the end of the swing, it's only 294. So when a swing is swinging, where is the likely chance of it breaking?
Bottom.
At the very bottom. There's a chance that it can break here. Like for example, you swing it more and more and more, and if this thing is not very strong, so if you're swinging like that, you're fine. Then you push more, push more. So if the swinging action is going on faster at the bottom, and faster at the bottom, the tension goes on increasing. Where's the tension going to be the maximum? In all the positions, right there at the bottom. So if at all is going to break, where is it going to break ultimately? At the bottom. And what happens after that?
Goes straight.
What happens if the cable breaks at that point?
Flies off.
It flies off. It flies off that way. And from there onwards, it's a horizontal projection problem, a projectile motion. So then you fly off and then land somewhere. You get it? Yeah, go practically into the situation and then you can think a lot of things. So I can ask you, like, where is it going to fall? Where is it going to land on the ground? If the ground is so much distance, if the string breaks, where is he going to be? So maybe I'll tell you the strength of the maximum strength that this can handle. So using the maximum tension that it can handle, you can figure out the speed at the bottom. And once you figure out the speed at the bottom, then it's a horizontal projection problem from there on, and just work it out just like how you done the previous problems, right? And you can figure out where exactly is the landing point. So a lot of things can be done that way. So you can see how the tension changes. So now if it is at some other intermediate position, it's going to be having a movement. There's a movement, which means the tension and these two are not going to be the same. It's not going to be the same. This tension is going to be bigger than that by mv squared over r at that point. Let me know if you have confusions anyway. So suppose you have at this point, the forces are still the same, mg t, mg cosine theta, the new theta, and this is the mg sine of the angle at that point. Are these two equal? No, because it's moving. It's moving with the speed. So obviously, this must be bigger than this to provide the centripetal force. So therefore, you'll be writing like this: T minus this is equal to mv squared over r. So the tension changes like that. Yeah.
What is the mg sine theta?
This one here.
Yeah.
That's what is actually making it go faster and faster in that direction.
Is that the acceleration of velocity?
That is the net force.
Oh, okay.
Not net force. The net force in that direction.
Okay.
Because there are two forces now, two net forces. One this way providing the centripetal force, and one that way providing the acceleration down. Because it's moving slower here, faster here, faster here, faster. The speed is changing. This is not uniform circular motion. The speed is changing. So at a certain location, you can just work it out just by using this equation. Okay? Clear? Any questions here on this? Now let's look into some of the problems. According to the conditions outside now, we'll work that out. So suppose you want to make a turn on a road. You want to make a turn on a road. And if the radius of the turn taken, the radius of the turn which you normally take, let's say, this is almost, so if you're going to go like that, so it's almost like 10 meters. So let's say 10 meters radius, and your car is 2,000 kilograms. Now this is the top view. This is the top view. You're looking from up there. 2,000 kilogram car is trying to take a turn like this. And 10 meter radius turn. And the coefficient of static friction between the road and the tires is pretty small because of the current conditions, right? 0.05 coefficient of static friction. So as this car is making the turn, what is the maximum speed you can drive at so that you will still be on the road? What's the maximum speed you can actually drive on the road so that you don't skid off? Okay. So look at the car now. How many forces are acting on the car as you move? 5 forces, exactly. There's one force which is a weight acting downward and the normal reaction upward, right? There's a traction force keeping it going this way, and there is a drag force pulling it back. And what's the other one? The friction. That is required for you to keep going in a circular path. But friction has limits. So what provides the centripetal force? What's the net force here? Friction. So the net force is friction and static friction. Now we are looking for the maximum speed, right? That means what? You're looking for a point when it's on the verge of slipping. So you're looking for the maximum static friction. What's the formula for maximum static friction? Mu s times normal reaction. Mu s times normal reaction. That is what the maximum static friction is. So the road and the tires, there is a maximum friction they can actually support you with. You can't exceed that. If you anticipate too much friction and go too fast, then it's going to skid. And we're looking for the maximum. So the net force acting on this car at that point is supposed to be supplied by static friction. And that net force is the centripetal force. Again, look at that statement. The net force is the centripetal force, but in this case is provided by friction. In this case, it's provided by friction. So the net force is provided here by friction. So solve it. You have everything right there. What's the normal reaction for the car?
1560.
So I'm going to solve it here, 0.05 times normal reaction. Isn't this the same as mg in this case? So I'll just write mg is equal to mv square over r. The normal force is mg because you're going on a flat road and you're taking a turn. So the normal reaction is just mg. And look what's happening here. What does that mean? What does that action mean there? What is it again? Does not matter on what car you're driving, how heavy your car is, whether it's a truck or a car, doesn't matter. Okay, are you driving a light car or Land Cruiser? Doesn't matter. All that matters is the coefficient of static friction between the tires and the road. So if you have the best tires on these conditions, you may get that much. Now if your tires are worn out, you can expect 0.01 maybe. So the maximum speed I'm talking about is for a good car. Good tire. I'm not talking about something that's very old and like 10-year-old tires. Okay, calculate it. 0.05 times 9.81 is equal to V squared. That's what we want to find out, over 10. So what is V equal to? Calculate it. Calculate what is V. How much? Cross multiply. 0.05, 0.5, 4.9. V squared is 4.9. What is square root of 4.9? 2.21 meters per second. Now, it doesn't make much sense for you looking at that number, 2.21 meters per second. Let's convert it to units that you use. How much is that in kilometers per hour? 2.21 meters per second. How do you convert it to kilometers per hour? Say it again. Times it by 3.6. Shortcut. I've told you this before. Changing from meters per second to kilometers per hour, just multiply by 3.6. Switching it back from kilometers per hour to meters per second, divide by 3.6. You get it? So multiply by 3.6. What do you have here? 7.97 kilometers per hour. Now, even kilometers per hour is not your common usage. So you want miles per hour. So divide this with 1.6. So when you divide this with 1.6, you end up getting in miles per hour, which is 4.9 miles per hour. Now that will help you to understand the speeds better. So next time you drive a car, drive at less than 5 miles per hour and feel how slow it is. And that is what you can drive on that road in those conditions. If you try to exceed that, what will happen is the road will say, you go to hell. I'm not gripping you anymore. Yeah.
What did you say that to get from kilometers an hour to miles per hour?
Kilometers per hour to miles per hour divided by 1.6. Okay. Because each 1.6 kilometers is 1 mile. Each 1.6 kilometers is 1 mile. So just divide it by 1.6. And if you want to flip it from miles per hour to kilometers per hour, multiply by 1.6. Yeah.
What is meters per second to kilometers per hour?
Times it by 3.6. So here times it by 3.6 and here divided by 1.6. Got it? And so you got 4.9 miles per hour, which is the speed. Look at the speedometer and see how slow it is. It's better to go slow and than be sorry. So you don't demand too much from the road, especially when it's black ice. It looked like a normal road. And that's the killer because the coefficient of static friction is pretty small. Even snow is much better. The loose snow is not bad. It will have better grip. But if it is icy, it's going to be much, very slippery. Even when you walk, you have difficulty walking because you won't have traction forward. So when you try to use the traction, it slips you. Your top part of the body is anticipating that grip, and so will start leaning. But the bottom part of the body slips, and so you slip and fall. And those are things that you'll see people ending up with. I think the road is not bad now because I think the temperatures have almost melted the icy thing. So it's not too bad. But if it had frozen on the road, then it would be totally different. After rain, and then it freezes, and that's the worst condition. Gosh. Okay. Any questions on this? So how fast you can go depends on the coefficient of static friction. That one right there. Now, on a normal day, you may be going at 20 miles per hour, but then the grip is much better. So on a normal day, the grip is much better, and therefore you can actually keep going on the road at a higher speed, and the road will support you. So you can't expect that support all the time. You always respect the road and your tires. Why you have issues with older tires is because, first of all, the tires are almost like hardened. It's not like really rubber. It's harder. Okay, so it's kind of hard. So therefore, it becomes more slippery. Plus, they don't have it's almost flat. No, flat in the sense like smooth. So when it's smooth, in addition to being a hardened rubber, it actually has very little support. That's why it is very easy to get off. So the best thing to do before the weather turns bad is to check your tires and see if it is old or smooth, or both. Checking the tires is very, 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 very important. Giving some more examples. Let's say you are, all right, let's say you're going on a road like this. When you're going on a road like this, pay attention. It's a road, and you're driving a car on the road, and you are right here. You're right there, and you're driving at a speed. You're driving at a certain speed on the road, and this is a kind of a hilly road. You can see so many hilly roads, especially in Indiana, right? Many hilly roads like that. All right, so when you're driving on that at that speed, maybe at a constant speed, how many forces are acting? How many forces are acting? Turn this way. Yeah, how many? 4. Okay, so what are the 4? The weight of the car acting downward, mg then. There's a traction this way, I'm not going to put it down. There's a traction this way, and there is drag forces backward. I'm not going to draw it on here because I'm not concerned about them because it's going at a constant speed, so I'm not worried about it, right? Because they are equal. Where's the other one? The normal force. Those are the 2 forces acting on the car, and of course the other 2 which I said I'm not drawing on it. So these are the major forces that I'm interested in, those 2 forces. Now what do you know about those 2 forces? They are equal?
Yes.
They are equal?
Yeah.
On a flat road they are equal. But are you going in a circular path?
Yes.
This is not a circular path for you? Isn't that a circular path? Yes or no?
Yes.
A hilly road like that, isn't it a circular path? Does it have a radius? Now, if it is a circular path, is your car going in a circular motion? Yes, no? Yes. What keeps your car going in a circular path? What is needed for it? A centripetal force is needed. In this case, what provides a centripetal force?
Gravity.
So what do you know about this and that now?
Gravity is greater.
Gravity is greater, has to be greater. There are only 2 forces acting on it. And out of these 2 forces, gravity must be greater. So mg is greater than normal reaction, because otherwise you won't get the centripetal force towards the center. Centripetal force is a net of these 2 forces. If the net of these 2 forces is towards the center, mg must be bigger. So mg minus normal reaction is equal to mv square over r. So what is normal reaction? What is normal reaction? Just flip it around. Make nr the subject of the formula.
MGR over
nr is going to be mg minus mv square over r. Is that clear? Good. So normal reaction is mg minus mv square over r. Just flip it around, you'll get this. Now let's discuss about this equation. What if you're not moving? What is normal force? Mg. Make sense? If you're not moving, it is mg. Now if you start moving on that hilly structure, what's going to happen is the normal force starts coming down, right? Because you're going at some speed, so there is definitely a quantity that's subtracted from mg. So the normal reaction is going to be smaller and smaller and smaller. The normal reaction is what gives you a feeling of weight. When the normal reaction becomes smaller and smaller, you feel like weightless. Have you felt weightlessness as you're going on a hill? That's what it is. If you felt like that on a hill as you're driving, that's because the normal force, unlike the normal mg right now, it is less than mg, at least for that moment. And that is why you feel lighter. Your car feels lighter. Now what if you start going faster and faster and faster? There will come a moment when this and this will be equal to each other, right? What's NR then? NR is equal to 0 when mg is equal to mv square over r. The NR will turn out 0. What do you mean NR turns out 0? What does it mean? That means the road is not pushing the car anymore. What does that mean? You're airborne. You're up. You're not supported by the road anymore. That means you're having complete weightlessness experience, which is basically like you're in free fall. Actually, you are in free fall. Now, if you go faster than that, then you will not just be over the road, but you'll just fly off. So if you go too fast, it's going to like take you off, like in the small humps and all that you see. If you go too fast, your wheel is going to come off from the road temporarily. But then it is only a small thing, so landing is not a big issue. But if it is such a hilly road like that, and if you go really fast, you will be off like a plane. But it's not a plane, remember. It is a car. Most of the weight of the car is right in front. So what will happen if you're airborne? Yeah, the front part is going to dip down. And not only that, the car's weight is not evenly balanced like a plane. One side, there will be more engine structure than the other. So once you're airborne, it not only dips down because the front part is more heavier, it also may tilt. And that is end of story. All right, so that is if NR is equal to 0. And so at what condition are you going to be taken off the road? Equate these two. If we equate these two, mg and mm cancel, so V is equal to square root of Rg. You cancel off m's, so it doesn't matter what car you're driving again. It is a speed that takes you off. So at what speed will you take off? If I'm giving you a radius, let's say if I'm going to give you a radius of, say, 20 meters, what speed, at what speed will you be airborne? Work it out. Square root of 20 times 9.8, which is what? 14? 14 point? Yeah, 14 meters per second. How many miles per hour is that? Now you know what to do. 14 meters per second, you're off the road. So times it by 3.6 and divide by 1.6. How much is it? 31 miles per hour on that hilly road is enough to kind of detach you from the road. Make sense? I enjoy doing this in between Dubai and Sharjah. There are two Emirates. You know Dubai. Sharjah is a neighboring thing, just half an hour driving distance. So when I go from Dubai to Sharjah, as we enter Sharjah, there are two flyovers. On the highway itself, there are two nice flyovers, which are kind of pretty steep enough. So I enjoy driving on those, especially to entertain my kids. So because my kids are there, so what I do is I pre-plan ahead of time and I slow down earlier before the flyovers, and I'm not asking you to repeat all these things, okay? These are just some experiments which I've done earlier. So I kind of free myself up because I want more room to kind of accelerate and go as fast as I can on that. At the same time, not breaking the rules, So I just give a little distance and then I drive. And when I come over here, I can feel myself almost like lifted off, and my children also like they feel, they enjoy that feeling. The car doesn't lift off completely. Well, I won't do that way, but it almost literally is there. So you can almost feel that the wheels are kind of, the shocks are almost open. You know, shocks are almost open. That means the car is free almost. So drive on that and then wait for the next one. Slow down and then speed up again. It's pretty close. The two of them are not too far away. It's like one after the other. So it's a nice thing. But there is risk on this one. Yes, I'm making sure there's no traffic right in front of me, but what if there was a traffic jam right there? Okay, that is bad. Because you don't even see what's happening on the other side, and then you're just going at high speed just to enjoy this, and suddenly you see that cars are kind of applied brakes and they're stopping. And first of all, you're almost airborne, which means the normal reaction is almost gone, right? And if at all you want to apply brakes and use friction, friction requires normal force. And you're missing that. And so there's no chance of stopping. So that's a risk factor there. But I don't go too fast. I just make sure that things are all right. Anyway, don't do anything of this kind to try out. So in any situation, this is exactly the line of thought. Draw the forces, find out the net force, and see if centripetal force is required. Another example, let me give you. A roller coaster. That's a roller coaster. All right, not very smooth. Now, a roller coaster, you're sitting in that car, and the car is going at a certain speed, and then it does this. So momentarily you are upside down, right? Let's find out what's happening. How many forces are acting on the roller coaster at that point?
5.
Yeah, whatever would be the force. Like, okay, there is a force that is, in fact, in a roller coaster, there's no traction force and all these things, right? It's just like free flow. It is not like driven. It may be driven elsewhere, but then when it is actually coming down like this and just rolling off like that, it is mostly by gravity. Okay, so when it goes like this and comes that way, tell me the force acting on it. One is and what else is acting on the roller coaster? Huh? Which way? Up? Down. The car is being pushed by the track. It's like this. Watch this. Think of this as your car. Right now, how many forces? Weight, normal force. And when it's making a circular path, did you see it upside down for a moment? See? It's upside down. So when it's right there, upside down, tell me what are the forces acting on it? Normal reaction this way. And gravity also same way. So what's the net force? All this is a net force. And that is what provides a centripetal force. So you write mg plus nr is equal to mv square over r. So what is nr? Yeah, don't memorize these equations because sometimes they kind of flip around, you see. So discuss those equations according to this. Net force is equal to centripetal force. So discuss in that manner. Look at this again. mv square over r minus mg.